Okay, in this short talk, I want to introduce you to some questions related to loss-of representation and teaching components. Before I start, I want to give you some new definition for K and loss-of representation. So in this new definition, our domain group gamma to be the finitely generated group. In the survey lecture, these groups are assumed to be word hyperbolic groups, but in this setting, we don't need to assume this. So for a general finitely generated group, representation is called K-analysis representation if there are constants A and B, positive constants, such that the K's largest singular value of log gamma over K plus 1's largest singular value of log gamma is bounded from below by the multiplicative some constant A times exponential of the word length of gamma. This is a very kind of easiest definition for the K-analysis representation. And associated with this K-analysis representation, I can define some other terminologies. For example, a representation law is a loss-of simply if it is K-analysis representation for some K. If a representation is Borel loss-of, a representation is Borel loss-of if it is K-analysis representation for all K, possible Ks. And a representation law is projective loss-of if it is one loss-of representation. And one fact that I want to mention is that if gamma admits an loss-of representation, then it admits a projective loss-of representation for some higher dimension. So in some sense, projective loss-of representation is kind of the most general loss-of representation. So given this definition, I want to raise the following question. So what are obstructions for gamma admitting loss-of representation? So the very first restriction is that our domain group gamma must be linear and word hyperbolic. Of course, there must be a homomorphism from gamma to a special linear group. And if this representation is an loss-of, then it must be faithful. So gamma must be linear. And what is more difficult part is that gamma must be word hyperbolic. Well, in our survey lecture, I always assume that the gamma domain group gamma must be word hyperbolic. But the definition that I gave you in this talk, I didn't assume that gamma is word hyperbolic. But at the end, this gamma must be word hyperbolic if it admits a loss representation. This is the very first kind of obstruction. And this Canary and Jubalis actually proved that if gamma admits a chaos representation, then its virtual cohomological dimension cannot be very large. So they actually gave a upper bound for the virtual cohomological dimension in terms of D and K, and the upper bound is given by D minus K. There are some finitely many exceptions, but this is the generic case. In the same paper, they actually proved that if gamma admits a project loss-of representation in dimension 4, they must be co-compact lattice in SL2C. And also, themselves and Subarles and Dai, they proved that if gamma admits a Borel loss-of representation in some dimension, then the gamma must be virtually a full group or a surface. So these are, I guess, known kind of obstruction for gamma admitting a loss representation, but there are still open questions. So the first open question that I want to introduce is the Sambarino's question in general. So this question actually asks that if a representation if gamma admits a Borel-Anderson representation for some dimension d, then gamma must be a virtually free group or a surface group. So the Canary-Tubalis and Dye results tells you that the San-Marino question is true for particular dimension d, but the general kind of statement is still open. And another interesting question is following. So as I mentioned, if gamma admits a projective Anderson representation, it must be linear and hyperbolic. But people suspect that there is a linear hyperbolic group gamma, which does not admit any Anderson representation in any dimension d. But the concrete example has not been found yet. So I don't know whether this particular assumption helps to solve this, find this example, find some count example or what, but suppose that our Gromov boundary of gamma is S2 sphere. Then we may ask, does this gamma admit an Anderson representation in dimension 4? Maybe it might be a very hard question because this question is directly related to so-called Cannon's conjecture, saying that if your hyperbolic group gamma has a spherical Gromov boundary, then it must be a virtually Kleinian group. This is very long-lasting, hard question, and if you can prove this statement, then combined with this Tubalis Canary result, you can actually answer the Cannon's conjecture. So it must be a very hard question, but still very interesting. Another question that I want to introduce is to ask some kind of global geometry of the set of Anderson representation. So for example, we don't know how many connected components does the set of Anderson representation have. Whether it's connected or not is still unknown. So related to this question, the following question is kind of more concrete. Like, is there a Borel-Anderson representation which is not hitching in even dimension? I assume that dimension is even because for odd dimension there is a counterexample by Thierry Barbot, and what he actually found is that there is a non-hitching Borel-Anderson representation in odd dimension. But for even dimension, this question is still open. So the next question is the following. So let's assume that our domain group gamma has a spherical boundary, say dimension d-3. And let rho be a projective Anderson representation in dimension d. And let's say C of rho be the associated limit map into the projective space. So I want to ask, what is the knot type of the image of this Cauchy, the image of the limit map? What is known is that let's say for example, gamma is a surface group that it has a circle boundary. Then for a Hitchin representation law, the image of limit map represents a non-trivial element in the fundamental group of the projective space. So in some sense, its knot type is kind of non-trivial. And to make this question more like traditional in some sense, let's lift our limit map to the sphere. So this is the universal cover of our projective space. And if we assume that the limit map represents a trivial element in the fundamental group, then we can lift it to the universal cover. Then we really have the codimension 2 sphere, SD-3 sphere in SD-1. So we really have the D-3 3 not in d minus 1 dimension sphere. So we can really ask whether this knot is on knot or represents some kind of non-trivial knot or not. So I'm asking this question because hopefully this knot type of our limit map may distinguish the connected components of the space of unstable representation. So that's why I'm kind of interested in this question. For the Hitchin components, I want to introduce this question. So let's say Hitchin of epsilon to be the set of all Hitchin representations such that there is some essential simple closed curve whose length is smaller than given number epsilon. And we take the, this is a subspace of the Hitchin component, and it's invariant under the mapping class correction. So we can take the quotient, and let's say m of epsilon to be that quotient. We may call this m of epsilon space the epsilon thin part of the Hitchin-Riemann moduli space. And in our talk, we actually showed that for some epsilon, if you remember, this epsilon is like the delta of n in our talk. The volume of this epsilon thin part is actually infinite, provided n is bigger than 2. So the question is for any epsilon and any n bigger than 2, does the complement, so-called epsilon thick part of the Hitchin-Riemann moduli space also have the infinite volume? Well, in the case of n equals 2, the classical case, there's the Mumford compactness theorem, which tells you that this complement is actually compact for any choice of epsilon. So we strongly believe that this question is true, but unfortunately, our kind of method of proof doesn't work for this epsilon thick part. So I think we need another clever idea, but I think this question is actually doable and must be true. Okay, this is the end of this talk, and thank you for the listening.